Now we're going to talk about a very basic way of how we can approximate integrals. So if we don't necessarily know all of the antiderivatives, how we could approximate it. And we're going to use something called Riemann sums, and this all has to do with rectangles. So here we're going to do an example of how we can estimate the area under f of x equals 1 over x, so that's our function, between 1 and 5. And what this is actually trying to estimate is the integral from 1 to 5 of 1 over x dx. And we'll talk about a more systematic way to do this later on where we're not drawing rectangles, but this is how we can approximate it. So first it says use 4 rectangles and left endpoints. So what we're going to do, I'm going to draw this graph. I actually want black. So here's our x-axis. We know the graph of 1 over x goes like this. Okay, and we want to go from x equals 1 to x equals 5. Now what we're going to do is draw 4 rectangles, since this is our directions, and we're going to use their bases along the x-axis between 1 and 5, and we want them to be equal length. So we find what's called delta x. And in general, delta x is b minus a over n. So this is your a, this is your b, and the rectangles is your n, how many rectangles you have. So in this case, our delta x is going to be 5 minus 1 over 4. So 4 over 4, we get a delta x of 1. So what that means is we're going to go a length of 1 and mark it off. So 1 to 2, 2 to 3. I am not doing this very evenly at all. Oh no. Okay, so we're saying here. Now we're going to mark off, so 1 to 2, 2 to 3, 3 to 4, 4 to 5. And you'll see that that gives us equal length bases. Now what we're going to do, this says left endpoints. So this is going to be the base of your first rectangle. You're going to go to the left endpoint, which would be here, and go up to the height of the graph. And then make a rectangle. Now the reason we like rectangles is that their area is really easy to find. It's just length times width. So the area of this rectangle, so if we say rectangle 1, the area is the length, or the width here, we'd say is 1 times the height. Now to get the height, it's where the function value is here, which this is the graph 1 over x. So this would be 1 over, plugging in the x value, 1. So 1 times 1 would be area of that first rectangle. For the next one, this would be our second base. And we want the left endpoint, so we're going to go up and plug in 2. So that height, this is a height of 1. We plug in 2 to get this height. This would be a height of 1/2. So our rectangle 2, the height would be, the base is still 1 times the height is 1/2. For our rectangle 3, our base is still 1. We're going to now, the left end point here is at 3, so we're going to go and plug 3 in. So this would be a height of 1/3 since our function is 1 over x. And then at 4, so this would be 1 times 1/3. And our rectangle 4, we'd be plugging in 4, so we'd have a height of 1/4. So a width of 1, the width is always the same, times our height of 1/4. So here we're going to we're adding the area of all of these rectangles. Okay, and we see that this is a little bit of an overestimate, right? We're going over. What we actually want is just the area under. What we actually want is just this. So we're going a little over, but it's an estimate. So this would give us 1 plus 1/2 plus 1/3 plus 1/4. And if you calculate that, you get 25 over 12. So our estimation here would be 25 over 12. Now, the next part is similar. It says use 4 rectangles and right endpoints. So we still have our 1 over x, okay, and we're still going from 1 to 5. And since it's still 4 rectangles, we would divide this up into 4, so we found that our delta x is 1. Now using right endpoints, we're going to say, okay, so our first base is here from 1 to 2. The right-hand endpoint of that is at 2. So we're going to hit the graph at 2. So this would be a height of 1/2. So our rectangle 1 here would have a width of 1 times a height of 1/2. Plus our second rectangle, we would go up at 3. So it would be still a width of 1 times a height of 1/3. Our third rectangle, we'd be going up at 4. So we'd have width of 1, height of 1/4. And the fourth one, we'd be going up at 5. So we'd have 1 times 1/5. So if we add this, we get 77 over 60. Now we see that this is an underestimate. So in part A here, we found an overestimate. In part B here, we found an underestimate. So we know our true area is somewhere between 77 over 60 and 25 over 12. Now, you can imagine there's a couple of ways that we can make our estimate better. Okay, so I'll show you one way here. Okay, so here's a simulation that will help show us. So here we've put in the function 1 over x, and this is showing that for left endpoints, left things, they found 2.08, which if you do our fraction is 2.08. Okay, and for right-hand endpoints, you'd get 1.28, which is what we found. So we know it's somewhere in between there. But what would actually happen if you took more rectangles? And you see if you take more rectangles, you're actually estimating it better. So see with 50, it looks like it's completely filled in. And fewer rectangles, right? If we only had 1 rectangle, it'd be a pretty bad estimation. We'd have 4. So the more we get, we see that this actually gets pretty close to 1.64. Okay, and if we had the right-hand endpoints, still not perfect, but they're a lot closer together. And what we could actually do, instead of taking the left-hand endpoints or the right-hand endpoints, we could actually take the midpoint of each one. So we would make our interval, and at the midpoint, we'd go up. So I know this is kind of small, but the thing you should be getting from here is that the more rectangles you do, the bigger your n is, the better estimation. And ideally what we'd want to do is take that limit of n down or up to infinity. Okay, so now obviously we can't do infinitely many or even a ton of rectangles by hand. So what we're going to do here is use 8 rectangles and use the midpoints of those rectangles. So this is going to get a little complex, but so here's our function 1 over x, and I'm not drawing it perfectly, but you know, it goes down like this, and we're still going from 1 to 5. Now our n has changed to 8, so we're going to look at our delta x. So we're going to take 5 minus 1 over 8, which would be 1/2 or 0.5. So here we'd go 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. Now for each of these bases, we now want to use the midpoint instead of to go up and find our height. So on all of these, our width is now 0.5, because that's how wide the rectangle is going to be. To get the height from each of them, we're going to plug the midpoint into 1 over x. Okay, and you can use the table on your calculator to help you with those calculations. So the midpoint between 1 and 1.5 would be 1.25. So we'd go up and hit the graph. And this height of this rectangle would be 1 over 1.25. So that first rectangle would have a width of 0.5 and a height of 1 over 1.25, which is the same as 4/5, or 0.8. Plus, so then our next midpoint between 1.5 and 2 would be 1.75. So we would plug 1.75 into 1 over x. So our width is still going to be 0.5. And if we do 1 over 1.75, we get a pretty crazy decimal, but it's 4/7. Okay, we're still gonna, so we're gonna get 8 here. So then we'd have 0.5, and we would plug in. So we've done our second rank. So now we'd be going between 2 and 2.5. So it'd be 1 over 2.25. Then we'd have plus 0.5, and we'd be plugging in the midpoint between 2.5 and 3, so 1 over 2.75. Plus 0.5, our next one would be 1 over 3.25. Plus 0.5, we're up to this one, so we'd have 1 over 3.75. We'd have plus 0.5, 1 over 4.25, and our last rectangle, so plus 0.5, 1 over 4.75. Okay, so I'm going to